point towards the north for you, which, especially if you're going into battle and it's kind of foggy, you need to figure out where you are and where you're going. That was pretty good. So way back then, they were even doing some things. This lodestone or magnetite was studied by the Greeks, and even Socrates wrote about it in about 400 BC. And even then, they were making some observations, some simple things you can do. So I spread some magnets around if you want to grab one of them. And there's some paper clips, and what Socrates was even studying back then was what you can do here is he noted that these stones, of course you got the magnets themselves, these stones would pick up little iron rods, and then those little iron rods or rings they would then pick up other stuff. So if you try that with paper clips, you'll see you pick up one clip and then one other clip picks up another one. So they were studying that kind of thing, back in ancient Greek times. Jumping up to about the 2nd century AD, the Chinese actually became experts at making magnets. So not just relying on these magic stones, they were actually making magnets all the way back in the 2nd century AD. And the way they did it, and we'll see later why that might actually work, is they would take iron rods on this magnetite or lodestone, and again, take some skill in artistry, but basically by stroking the iron rod over and over the same direction on the magnetite, you could turn that iron rod into something that was magnetic. So that was actually quite a while ago that they were even making those. Next thing I could find was jumping all the way up to about 1100 AD, when the compass, which was developed over in China, came to the west. So what's up with 1100 AD with your well-rounded liberal arts background? Why would a compass come to the west in the neighborhood of 1100 AD or so? What was going on in the west before that, and what was going on in the west after that? Or what eras were those? What's before 1100? What's going on there in Europe? What kind of age was that?
There's a lot of explorations.
What'd you say? I missed that.
Explorations and crusades.
So back before 1100, not a whole lot going on here. That was the Dark Ages. So not a lot of science, math, art, things like that were going on in Europe. Where was all that going on? Through the Middle East and over in Asia. So what's the era after the Dark Ages in Europe?
The Renaissance.
Renaissance. Now here comes math, science, art back to the West from other cultures. And so it was right about that 1100 or so when all that stuff was starting to happen. So people started to move around. Things from the Asian cultures, Middle Eastern culture started coming back over to Europe, and the compass was one of those things that came over. In 1269, Peter de Maricourt, who was a French engineer, was doing some exploring and came up with some things that we still use today that you learn about probably when you're in kindergarten, but it comes from de Maricourt's work. What he did is he was using compasses to guide tunnel building. So you're digging through building tunnels, you kind of have to still know which direction you are, so you can use compasses to do that. So he was kind of fascinated by that. So he did some studying and took some magnetite and would shape it into different things. And he would make like little spheres of magnetite and put little needles around it. Probably doesn't work great on these, but we'll see something else in a little bit. But he could put little needles around it and watch which way they wanted to point, and found out that there were two special locations on his magnet. And so he designated them, like we still do today, as two different poles. Then he studied the interaction between poles. And it was 1200, so it's kind of interesting how he did this pretty easily. Is he marked where the poles were based on how the needles lined up, and then he would put them in a little bowl and then float the bowl in water. Then he'd bring two of them together. So why stick them in a bowl and float it in the water? They move around now. They can spin, So you bring these two together and watch the interaction between the poles, and probably again played with this in about kindergarten. So what did he find happened with like poles? Yeah, what did like poles do? Repel. What did unlike poles do? Attract. And again, that's what they were figuring out in the 1200s. Jumping all the way up to 1600, Gilbert suggested that the Earth itself was a big magnet. So what was really happening with these compasses that they've been playing with for so long was that compass was a magnet being attracted to another magnet, the Earth itself. That's why compass needles were moving around. And then he probed around magnets with a compass. And you can do that. You can take one of the magnets, have a compass around it, move the compass around, and you'll see the needle moves. And if you study how that needle moves, what he found, and these were kind of the terms he used, is that there were rays of magnetic virtue that were spread around that magnet. So there's some kind of magnetic virtue around the magnet that around the magnet that the compass was picking up. In about the mid-1600s, Descartes came along and figured out a way to map out those rays of magnetic virtue, and we can even reproduce what he did. So I put some pieces of paper with some clear plastic on top. You put your magnet between the paper and the plastic. This way, you'll see why. And what we'll do is map out the rays of magnetic virtue by taking some iron filings. And what we're going to do is, but before we do this, before you go any further though, since I know we've got a classroom full of people who lick batteries and eat potatoes, can you read the warning on that bottle, please?
Not for human consumption.
Got that?
Those tables over there.
Don't eat it. So I spread some iron filings around. If you hold them, maybe about a foot high, and just start to sprinkle like you're salting the paper. Just kind of sprinkle around and see what we see. So the plastic is going to let us recover the iron filings. So don't dump them, just kind of sprinkle them around and see what happens. Starting to see rays of magnetic virtue showing up.
I see a circle.
In fact, this led to the concept of what you're actually seeing are magnetic field lines. You can actually visualize the magnetic field around that magnet. Of course, I had you sprinkle those on a flat surface. Take a look, especially at the ends, at the little iron filings. You notice they're doing something kind of funny at the ends? See them sticking up? You know why they're sticking up?
There's an earth above us.
So, keep in mind that magnetic field is not flat. It's a three-dimensional field around that magnet. Those iron filings are trying to follow those field lines. It's just that with the weight of them, they'll get pulled back down. I do have a way to actually see the three-dimensional field with this little device. So this has some sort of oil in it with a bunch of little iron filings in there. So you'll have to do this every once in a while as I pass it around. I'm going to shake it up to distribute those iron filings through there and stick a magnet in the middle. And those iron filings will line up with the magnetic field lines. And so as I pass that around, you can get an idea of what the three-dimensional field looks like around there. And you can even play with this. If I pull it part way, you can see what the field looks like around the end. So it'll just take a little time for them to line up. And again, you have to shake it to distribute a little bit more. But it's a way to kind of visualize what the field looks like, or what those field lines look like that we're going to draw on the board to kind of picture things. Because those iron filings line right up with them. So again, they were studying that actually quite a while ago without a great understanding until we figured out the concept of fields. A big step in our understanding of magnetism came in the 1800s by Oersted. We're going to come back to this, but just for now, Oersted discovered that currents will give rise to magnetic fields. So we'll come to that later, how all that works and what really causes and produces magnetic fields. So that's coming in here in a little bit. By the way, on these fields, a way we could draw that is if I've got a bar magnet like this, and if you're going to try and represent that magnetic field that you're seeing in that little thing going around, this is the North Pole, this is the South Pole. If I'm looking at just the field on the outside, the lines would look something like this. Maybe something like that. But as we saw with electric fields, these field lines have direction. Anyone know what direction they go from which pole to which pole? Yeah, give you guys a 50-50 shot at it.
Did I get it right?
No. Out of North Poles into South Poles. So out of North into South. So mentioned that they figured out early on the Earth itself is like a great big magnet. Almost as if, it's not really, we'll talk a little bit more about where this comes from in a bit. Almost as if there's a bar magnet in here. So you get these magnetic field lines in a simple version. We'll talk about that here in a second too. Here's those field lines coming around. Except for something interesting. You'll have to separate these away from the magnets that are around your cables. But if you take those compasses and get them away from the magnets, as we stand here in the room, which way is north? You guys know how to read compasses? Make sure they're away from the magnets. Yours is near something.
She's got hers over here like this.
Make sure you get her ways away. I boosted these magnets this morning. We'll explain how I do that and how that works later. So make sure you're away from those magnets. So which way's north? That way. Okay. How did you know that?
Because I lived here. I'm good with right orientation within the area.
Just go use over there. So for most of the class, the red arrow pointed that way, except for you guys.
Well, she screwed that up. She's
You
like.
guys have a black arrow, right? Points that way, right? So you said that's north, right? Put that compass by the different poles of your bar magnets that are marked. What does the red arrow, or for you guys the black arrow, point to? Yeah, what's the red arrow point to? Which pole? The south pole?
Yes.
Wait a minute, so is that south?
Technically, you go all the way around the Earth.
So notice that compass needles point along the direction of field lines. They line up with the magnetic field lines and they'll point right in the same direction as the field. So which way are the magnetic field lines of the Earth pointing? That way, right? Which is geographic north. If this were a bar magnet producing it then, and here's geographic north, is this a north or south pole down here, magnetically? It's actually a magnetic north pole here, and a south pole there, and here come your field lines, like this. And sure enough, that magnet will line right up with those guys. So it's like an upside down magnet inside.
So did we just, so did it end up becoming, did we end up calling it the North Pole just by convention before?
Oh, it's for since ancient times considered
Right.
geographic north.
Right, but we came up with geographic north before we came up with magnetic north?
Well, and is that always magnetic south?
That is a good question.
In fact, over history, our poles have flipped. Our magnetic poles have been flipping. That has not always been magnetic south. How do we know the poles have been flipping over history? It's over geologic history. It's a really cool record of it, actually all around the earth, but a really nice record on the seafloor where there's a crack in the seafloor with lava flowing out. So lava pops out, and if it's got any magnetic component in it, those little magnetic pieces are gonna line up with the field lines. It's in lava, which is a fluid, so they can move around, they'll line up with the field lines. But what happens to lava as it seeps away from that crack? It hardens, locks that stuff in place. And then it continues to expand out like that. So there's a nice record on the seafloor. As long as they can date that rock, they can see, oh, this rock dates at this time, look, the magnetic field is pointing this way. Oh, here's a different date, oh, man, it's pointing the other way. You can actually track how our magnetic field has been flipping back and forth over geologic time frames. In fact, I'll show you a couple of quick pictures here. Just a sec. Find it here. There we go. Here's just a better sketch of a magnetic field around a bar magnet. And actually, this does show that the field lines do go through the magnet itself. They don't just stop at the magnet. So this would be kind of a sketch of a bar magnet. Here, let's see. Here's a simplified version of the magnetic field around the Earth. So again, it's as if there's a bar magnet in here where the North Pole points down, the South Pole points north, and here are your magnetic field lines. It's not quite that simple because of the influence of the sun. So I think this one's oh no, I was gonna show you this. So I mentioned that over geologic time, the poles are flipping. During our times, the exact location of that North Pole, or the magnetic pole up in geographic north, I should say, moves around a little bit. Actually, if any of you heard that's been in the news lately, there've been some little science stories about that. So I found a little picture of where the exact magnetic pole is. So here's Canada over here. Here's geographic north, right there. And over about a century, the exact location of the magnetic pole has been moving this way. And what's been in the news is if you look in 20-year increments, here's movement over 20 years, here's the next 20, next 20, next 20, and then the next 20, and then here's our next 20. So they've been talking about how that motion's been accelerating. So whether that means anything, I'm not sure, but they have been tracking this for a good 100 years as far as where that exact pole is. So it's not a fixed location, it does move around. And we'll talk about why the Earth would have a magnetic field and what causes that in just a bit. Let's see. How about, let's see, a magnet like this guy here, of what the magnetic field would look like around, say, a horseshoe magnet. And specifically what we're gonna be interested in and be able to use is what's going on right here. Well, fortunately, unlike when we were talking about electric fields where it was hard to see things, now we can see it. So if you guys can do this for me. Y'all wanna come over here for a second just to see, sprinkle around this area. What I'm interested in is like right in here what's happening, a little bit higher than okay, so in between, what happens? Depends on which is the North Pole. So let's see. Is that the North Pole? If this is the North Pole and I see my little iron filings like that, which way are those field lines running? Right like that. So that's what's kind of nice about magnetic fields is we have a nice way to picture them. So head back to your seats for a sec. So here's again kind of a better sketch of what that might look like. Again, here's just another version of a bar magnet. And a lot of times you see these drawn like this where they don't continue the lines into the magnet itself. Here's what it would look like around a horseshoe magnet. Specifically, what we're going to be interested in is this region here that we can get a magnetic field that runs that way. So we're going to use that here in just a little bit. So, interesting thing is what happens when you introduce charged particles, like we've been talking about, into magnetic fields that we are talking about now. And I'll show you just a simple example here. So this is an old oscilloscope that is supposed to be used for other things, but we're going to use it for a specific thing here. What this does is, back here it generates electrons, puts them through a potential difference like we talked about that will accelerate those electrons this way. And what you see that little spot right there? What you're seeing is when those electrons hit the back of the screen, they're fluorescing the back of the screen. That lets you visualize where the electrons hit. So what we've got are charged particles, electrons, and they're moving. They're moving this direction at this point. If you've got moving charged particles and you stick them into a magnetic field, they can move around. Well, if that magnetic field is making that little spot move, first semester physics, that must mean there's a force acting on those charged particles. And sure enough, magnetic fields can apply a force to moving charged particles. So let's take a look at that a little bit. A couple different ways, both quantitatively and qualitatively, of what's going on with that. Let's try it this way. Let's just jump right to this. We've got a new force now to add to our list, a magnetic force that is going to be applied to moving charged particles. So what that's going to be related to and how strong that force is, it's going to be on a charged particle, so you need to know the charge. The charges have to be moving. The way we can say that is, here's the velocity of those things. It's going to be based on how strong the magnetic field is that it's flying through. And I did look this up. And I saw it on the internet, so you know it must be true. So we're going to use the symbol B for magnetic field. I think where that comes from is way back when they were studying fields in the early days, they labeled different fields, field A, field B, field C, field D, field E. Later found out some of these are really different manifestations of the same thing. I think just from way back then, it was magnetic fields that had been designated B. And I think that just stuck from what I heard. Whether that's 100% true or not, I'm not sure, but at least we're stuck with it, that that's what we're going to use to say magnetic field strength. And then here's one other piece. Something about an angle. Well, that's got to be the angle between two things. Which of these things has direction to it? Magnetic fields have directions. We just talked about that from north to south poles. What's the other one that has a direction? Yeah, velocity has a direction. Does charge have a direction? You don't say like 5 coulombs to the right. So notice what that is. It's the angle between the direction of the magnetic field lines and the direction that that particle is flying through those field lines. Here's where it gets even more interesting. Is this part you don't have to know, but I just want to see if any of you do know this. Here's a real formal way to write what I just wrote up there. It's a little bit more compact way to write this. As a cross product. Any of you familiar with cross products?
Cross multiply and divide.
It's a shorthand way to say this times the sine of the angle between the two. If you've seen this before, you also learned about dot products. Dot products are this times that times the cosine of the angle between the two. It's too bad you don't know about this. But since nobody does, we're not going to do it that way. We'll do it a different way. What's kind of interesting, but again, this comes from cross products, is this also has a direction. Forces have direction. The direction of the velocity, direction of the particles flying, the direction of the magnetic field, and the direction of the force applied to that charged particle are all perpendicular to each other. And since you don't know about cross products, we're going to learn a different way to tell what is the direction of the force acting on that charged particle. So let me give you some examples. If all 3 of these are perpendicular to each other, that means when we try and draw pictures on the board, we've got some stuff that might go that way, some stuff that might go that way. Well, that's no problem on a board. But then something may pop out of the board to get 3 things perpendicular. So we need to come up with a way to sketch something going into the board or coming out of the board. And an easy way to do that is with this notation. So what I'm going to do is draw a magnetic field. Actually, I'm going to do 2 different magnetic fields in different regions of the board. Here's one. Where I'm representing magnetic field lines, and here's another one where I'm representing magnetic field lines. One of these representations are field lines going out of the board. One of those representations shows field lines going into the board. Which is which? Again, you have a 50-50 shot here. Any guesses?
Is that out? And out.
So, when we're showing directions of things, so we did this way back when we showed like velocities. What little thing did we draw to show that velocity? So let's say I had a little car here. Now we're going to sketch something to show velocity to the right. What did I draw? I drew a little arrow, didn't I? I didn't add this part, but I'll add that part to it. We drew arrows to represent things moving in directions, right? That's what these are supposed to represent, are arrows, field lines. Just like we drew electric fields with little arrows. When you look at the back of an arrow, what's on the back side of an arrow? Feathers, right? Deflecting. When it's coming to you, what's on the front end? Little pointy thing, right? So, what's this?
Back end of the arrow.
Well, what's this? That's supposed to look like the little fletching, the feathers in the back. So that says we're going into the board. This is like a little pointy part coming out at you. So it's this out. I will always try and do this. So you're supposed to be able to just recognize by dots or crosses. I usually, even though it's redundant, write that in there just so it's clear that this is magnetic field out, this is magnetic field in. Let's say we send a charged particle into this field, and I'm going to do it this way. We've got a positive charged particle, and I'm going to make it fly that way into the field. Once that moving charged particle enters the field, it's going to have a magnetic force acting on it. How strong? Its charge times its velocity times the strength of that magnetic field times the sine of the angle between these two. By the way, if this is perpendicular to this, what is the sine of that angle? What's the angle? 90 degrees. What's the sine of 90? 1. So as long as everything's perpendicular, then that part just turns into a 1. Now the direction part. What we're going to do is learn the first of your right-hand rules. I'm going to show you one way to do this. If you happen to have learned this another way, that's fine. I won't show you the details, but back when I learned this, we learned it with 3 fingers like this, or 2 fingers and a thumb. So here's 3 things perpendicular to each other. There were, I think, 2 issues with this. It works like charm. It just got hard to remember, what does this finger represent? What does this finger represent? What does this thumb represent? And maybe it looked too much like gang symbols. So we're going to do it a different way. That makes it a little bit easier to remember what things look, or what's what.
I remember.
One quick thing though, anybody in here left-handed? If you are left-handed, you actually have an advantage right now. The rest of you, when you're taking a test and you're under stress, please put your pencil down before you try doing right-hand rules.
I remember.
People tend to use the hand without the pencil in it.
I remember my mom told me horror stories about on physics exams.
Yes.
She did that.
It's right hand. Put your pencil down. Okay, here's how we're going to do it instead. So you're going to have to hold your hand this way, rather than the 3 fingers thing. We're going to do it this way. And hopefully this all makes sense. When you think of drawing a velocity vector, how many little arrows do you draw? A single arrow, right? I've got a single thumb sticking out here. So that's going to be our direction of the velocity. When you drew field lines, we did electric fields before, now we're doing magnetic fields. You do just a single line to represent a field, you draw a bunch of them, don't you? Here's a bunch of them. So these fingers are going to point in the direction of all your magnetic field lines. When you first learned about a force, we said, oh, it's a push or pull, right? Which way do you push? With your palm, like that. So your palm's going to be in the direction of the push or the force acting on that particle. So let's try that with this one and see which way is that particle going to be deflected by that magnetic field. So make sure it's your right hand. So here's the direction of our velocity. So which way does your thumb go? Thumb's got to go that way, right? Your fingers are the magnetic field. Which way do they point? They go into the board, right? How do you keep your thumb that way and your fingers that way with your right hand? Notice you have to flip your hand like that. So which way is that particle going to get pushed? Up. And sure enough, with this setup, this will have a force on it that's going to make it go up like that. How about this case? What if I send a positively charged particle flying through a magnetic field that way? So my thumb needs to be pointing this way. Field lines are out, so I need my fingers that way, out of the board, towards the back of the room. And which way, by the way, this is good fun for me to watch during a test. So which way does that particle get pushed? Down. And notice I've got 2 different fields, same kind of particle, so hopefully we suspect it would go that way. So far so good? So we'll add one complicating factor. there's two kinds of charges. So what do we do if it's a negative charge? This is the only thing to be careful of. I guess to me, the easiest way to do this is what we just talked about was set up for a positive charge. If it's a negative charge, flip your thumb opposite the way it's actually moving. So thumb goes in the direction of positive charges, but opposite the direction of negative charge. So the way I would do this, hopefully it's intuitive that it should go the opposite way. So let's see if that actually works. So I've got a charge moving to the right, but it's a negative charge, so I have to flip my thumb the opposite way. I need to get my fingers pointing the same way as the field, with my thumb pointing that way, opposite the way it's moving, and notice now, sure enough, my palm tells me I'm going to push it down. So that's the only thing to watch is with the negative charges, you have to flip your thumb the opposite direction. So now I'm going to test you. And I need you to be able to see this pretty well. So you see that little spot there? Let me try and change this a little bit. I'm going to fuzz it a little bit so it's a little bit bigger and adjust where it is. Okay, so you see where that is, right? And again, what that's being produced by are electrons going this way. So I've got charged particles flying that way that are electrons. I've got a magnet here with a north pole and a south pole, one of each here, which means I've got a magnetic field going either this way or this way. So let's try it this way first. I've got a north pole here. So let's try it like this. I'm going to hold the north pole on this side. When I bring this magnet up to the screen, which way is that spot going to move? So again, I'm holding the north pole. I'll do it right like this. So which way is that spot going to move? All right. Which way is the field running? From north to south, so my fingers better be that way. What do I do with my thumb? So I've got charged particles going that direction, right?
They're negatively charged.
They're electrons.
So you want to put
So
it
I need to make sure my thumb's the opposite direction that they're actually moving. So particles that way, but they're negative, so thumb the opposite way. So which way is it going to move? It says, should be a force up on it. Okay, let's see if it actually works. And here it goes up. Okay? Everyone okay on that?
Yeah.
All right, so here's your test. Is the North Pole up or down right now? Let's say. Is the North Pole up or down? Y'all see the spot? Spot went that way. Which is North Pole, up or down? So how do you figure this out? Which way is your thumb going to point? Opposite the direction the particles are moving, because they're negative particles, so I better have a thumb that way. What's the direction of the force? It pushed it that way, right? So I better have a palm pointing in the direction it got pushed. How do I have my thumb pointing in and my palm pointing that way? How do I hold my hand? Like that. There's my thumb, opposite direction moving, there's my palm pushing. What's the direction of the magnetic field? Down, and do fields run from what to what? From north to south, right? So which is the north one? And I have not looked, I have not checked, and I spun it so I couldn't even influence it, so. Right. So that was the north. Megan's intensity. So, here's some more interesting stuff. What if our field is big enough? Let's change this back to a positive particle. So now it's going to go up. What if our field is big enough as this enters? So it starts curling up like this. Let's stop right here. Here's my little particle. It's now flying that way. What's the direction of the magnetic force on it right now? Positively charged particle, field in. Oops, now we're going up. Field in. Which way is it getting pushed? Back that way. What's going to happen to the actual path of this thing as long as the field's big enough it doesn't escape the field? Started by getting pushed up, now it's getting pushed left. What kind of path is it going to take? It's going to make a circle, as long as I can keep it in that field. And I can start to get it to circle around like this. In fact, if I look at some details here and want to quantify some things, we can go back to some really basic first semester physics and notice that magnetic force, well, let's go way back. If I add up all the forces acting on something, it's mass times acceleration. The force acting on that thing is a magnetic force. Now, don't have to worry about the sine theta part because the direction it's flying and the magnetic field are always perpendicular to each other. That's equal to mass times acceleration. If you remember how we represented the acceleration of a particle or an object when it's going in uniform circular motion, that's when we switch that right-hand side to mv squared over r. So here's the acceleration of that thing. And if you solve that for the radius of that path, it's actually pretty easy to figure out. Depends on some properties of the particle. What's its mass, what's its charge, how fast was it going, and what kind of magnetic field did you put it in. And that's going to fix the radius of that path. So actually pretty easy to figure out. What happens next, let's say we fire that into the field, except we're going to do this. Rather than fire it right like this, where if we did this, all it's going to do is sit here and circle around. What if instead we fired it in like this, with a little bit of a component out that way to the velocity? Remembering I'm trying to draw three-dimensional stuff on a two-dimensional board, so remembering that there are field lines like this. So what's going to happen if I give it an angle out like that so it's got a component to the velocity this way? Enters the field, tries to circle around, but what does it mean when I've got a component that way? We can actually get that thing to start spiraling down these field lines. So it's got the circular part, but it's also going to travel right along those field lines, spiraling like that. Got a couple interesting things with that. One, let's do this one. Let's see which picture I've got for this. Here's a little bit, it's a little more dramatic. Not to scale, by the way. It's going to be a little bit small. Picture of what the magnetic field really looks like around the Earth because, again, they're going to make this extra dramatic. But our field's actually getting distorted a little bit by the solar wind. So as that's popping up, I'm going to draw a more simple sketch over here. So let's say here's the Earth. Let's draw a little magnetic field. Let's draw a few of them here. without the distortions that you're going to see there. The Earth, I'm sorry, the sun is actually quite active and spits out all kinds of stuff that we kind of lump into that term solar wind. A lot of what comes from the sun towards us are charged particles. So we get this big bunch of charged particles. Here it comes towards the Earth. What happens to those charged particles when they hit the Earth's magnetic field? Exactly what we just talked about. They start spiraling down those field lines. Anyone know what causes northern lights? Anybody have seen northern lights? We got Canadian, or I mean not Canadians. We got Alaskans in here. All right. How many have seen northern lights? Oh, it's too bad. That's it. Anyone know what causes them? You learned about that like in kindergarten, right up there. Well, let's see. Let's build up to it. Okay. Let's do this to figure it out. Let's take a look at something else. See, I guess I don't need that picture up there. What happens if I make a magnetic field that looks like this? And I'll just draw 3 of these lines. So kind of an odd shape there, kind of a bulge. So again, this is going to be 3-dimensional, so I'd have another field line out like this and another one behind like that. So we'll just do a look at a slice here. And what we'll do is we'll send a charged particle spiraling into this. So down the lines there somewhere, we sent a particle in, so it's spiraling down these lines. I'm going to try and get some 3-dimensional to this. So this is out of the board, into the board, out of the board, into the board. And here it's spiraling in like this. Let's stop right here. So right at that spot, again, a little hard to draw in 2 dimensions. This is where our particle's going straight into the board. So I'll try and represent it like this. Here's our particle, and the velocity is now the one straight into the board. If I've got a velocity into the board, and a magnetic field, just like we saw with electric fields, the direction of the magnetic field at any point along the field line is tangent to that line. So here's the direction of my magnetic field at that point. What's the direction of the force acting on that particle? Did you get this way? So, field like that, thumb into the board, it's pushed that way. Got it? We'll let it spiral some more and take a look right here. So it comes around and we're right here. So again, our particle at this instance going into the board, here's our magnetic field. What's the direction of force now? You get it back this way. Notice the strength of that magnetic force is this. What's the one piece of this that's changing as our particle goes across here? And how can you tell? I should do that. Which of these are changing? You're getting good. Which of these is changing? That makes that change. How do you know that's changing? It's not that. Well, maybe, depends on which. We looked at field lines before. What does the spacing of field lines tell you? When field lines are close together, what does that tell you about the field? Strong. If they're further apart, weak. Notice that on the ends is where my field is the strongest, which means as my particle gets towards this end, that force is getting bigger and bigger because the magnetic field is getting stronger and stronger. And notice with this shape, what happened to that force we applied to that particle? Notice it always has a component pointing back towards the center of this shape. And the further this thing gets towards the end, the stronger that force is trying to push it back to the center. In fact, if we adjust this right, here's a way we can trap a particle in a vessel, so to speak, with no walls. We can take a charged particle and trap it and make it stuck in here going back and forth without any like physical barriers holding it. That sort of makes sense? Because if it does, let's look back here. Here comes our charged particles from the sun. They hit that magnetic field, which extends well beyond our atmosphere. This isn't probably even to scale. If I were to show our atmosphere, it's maybe like this. So here come our charged particles. They go spiraling along, and they follow these field lines. But what's happening to the strength of the magnetic field as they're following these lines? It's getting stronger and stronger and stronger, and eventually strong enough to push them back the other way, and we can get those charged particles, rather than bombarding us, they get trapped out here and just spiral back and forth. But what happens if we get a particularly energetic burst of charged particles from the sun, strong enough that they can fight their way even further along these field lines? Where are they going to enter the Earth's atmosphere? Where geographically? Up here in the north, or down here in the south. And what happens when these energetic charged particles from the sun smack oxygen and nitrogen in our atmosphere? They make the oxygen and nitrogen glow. In fact, I can even give you the colors here. When you see green, that's coming from oxygen. If you ever see red, that's from nitrogen. Most of the time around here, you'll see white, and that's just because it's too dim to actually have the color show up. Up in Alaska, you see the greens and reds, don't you?
Greens.
Mostly greens, because mostly oxygen that's doing the work. But this is why you see them in the north, because that's where those charged particles are going to enter. You've got to have a really energetic burst for us to see them as far as south of spearfish, where they can get in all the way down here. Is there such a thing as southern lights? Oh yeah, absolutely. Same thing, just comes and enters down here. So that's what causes those. And one last little thing before we take a break. If you do know this, don't say what it is. But how many of you do know there's something special about wintergreen lifesavers? Don't say anything though. Just let me know if you do know that there's something. Something special about wintergreen lifesavers if you chomp them. Hold hands up so I can tell. Is that really it? For real? Holy cow. You guys want to see some northern lights? I'll show them to you.
I remember this now. I remember this now.
So check this out. You take a lifesaver. How do you know this, by the way?
Somebody told me.
Oh, you've never seen it?
No, I've done it before.
Oh, okay. What we're going to do is crack a lifesaver. A wintergreen lifesaver. And when you do that, when you first crack them, what you do is you break a sugar molecule, and you end up with a charge separation. And of course, they don't like that. So what will happen is that charge will hop across this gap to take care of that charge separation that you made when you first crack that molecule. Hey, wait a minute. That's charged particles flying through the Earth's atmosphere. When those charged particles smack into the oxygen and nitrogen, they'll make that oxygen and nitrogen emit light. Just like the northern lights. So for those in the know, does it work with butterscotch? How come it only works with wintergreen lifesavers? How energetic do you suppose that little charged particle is flying through the Earth's atmosphere compared to something coming from the sun? Not very. Yes, it does happen like we talked about. This will smack into the Earth's atmosphere, oxygen, nitrogen. They will emit light. That we'll talk about light later in the semester. But that light is at too low an energy for you to be able to see, unlike real northern lights. Or if you bit a butterscotch lifesaver. So what's special about wintergreen lifesavers? They have an extra chemical in them. It's oil of wintergreen. And what happens is, it's one extra step compared to actual real northern lights. The photons, the light that's emitted by the oxygen and nitrogen, hit the oil of wintergreen, and it's the oil of wintergreen that then emits the light that you can actually see. So as we take a break, you guys want to see it? So let's do this. We're going to take a break. I'll take you probably table by table, and why don't you guys, you can join them, because we need to go where it's nice and dark. So I'm going to take you right across the hall in our little storage room. See what this might do. Let's make something like this. Let's say we've got some parallel plates that we put some charges on. So we've seen that before. So we've got an electric field. What's going to be different is let's immerse this in a magnetic field also. And let's make the magnetic field like this. Into the board. Then let's send a charged particle, let's make it a positively charged particle, flying through there. So they're straight through. So what's our charged particle going to do? If all we had was just the electric field, what would happen to our particle? It would go down, right? I'm going to draw them here, even though it actually happened there, but just to make our picture clear. Just due to the electric field, right? If all I had was the magnetic field, and I fired that particle that way, what would happen? There's a magnetic force up, right? Everyone okay with that? How would we figure out how strong the electric force was in terms of the field? We've done that before. If we want to know how strong is that magnetic force up, we just looked at that. So what's the real answer as far as what our particle's going to do? It depends. Which one of those forces is stronger? But here's what we can do with this. Let's add one more piece. What if on the other side of these fields, I put a little barrier with a little hole oriented where a particle would go right straight through, so that the only particles that go straight, or that go, I should say, the only particles that are going straight are the ones that are going to get through our little hole here. We've just made something kind of useful. In fact, what is the criteria for our particles to go right straight through? What does that say about these two forces? They have to be equal. So for this particle to go straight through, I know these forces have to be equal, which means these have to be equal. Notice it's the same particle. And so here's how fast that particle's moving. It's just the ratio of those two electric fields. Which means if I know how strong my electric field is, that's not so hard to do. If I know how strong my magnetic field is, which isn't too bad, I know how fast those particles are that are shooting through that little hole. What happens to any particles going, let's say I set my electric field, set my magnetic field, fire stuff through. What happens to any particles that are slower than this? If I send that in slower, does that impact the electric force? Nope. Does it impact the magnetic force? Yep. If I make the velocity slower, what have I done to the magnetic force? That gets lower. That gets lower. So which force is bigger now? This guy, because I haven't impacted that. So what happens to my slower particles? They actually get deflected this way. And they don't go through. What happens to faster particles? If I fire them in faster, I haven't impacted this at all, but I've made this force bigger now. And so my faster ones get deflected up this way. So notice I can fire all kinds of particles in here at whatever speeds I want. But only one's going to make it out the other side. And which one? I can select which one I want by adjusting my fields. In fact, what we've just made is called just that. It's a velocity selector. When you get those like homework problems where they say, oh, a particle's going 2 times 10 to the 6 meters per second, that's how they'd actually do that. Fire a bunch of charged particles through a velocity selector, and by adjusting the field, you can pick what velocity you want popping out the other side. Any other speed gets blocked off. It either hits high or low. So a really nice, simple way to get an exact velocity on charged particles, moving at those kinds of speeds that we've seen. I'm going to jump ahead here just so we can watch some videos to finish up today. We'll go back and kind of build on this and look at some other devices next time. But we'll come back to this part too, but I'm going to just add one quick thing here. We'll see where this comes from later. We're going to find out that ultimately what's going to produce magnetic fields are moving charges. So we'll see what that's all about later. And we've already talked about how currents going through wires are moving charges, which means if I send a current through this wire, I will get a magnetic field around this wire. We'll see later the details of this. I'm just going to jump right to it for now for this next example. Really easy way to figure out the direction of the magnetic field around a current carrying wire. It's another right-hand rule, but this is an easy one. Let's say I've got a current running this way through my wire right now. If I want to know the direction of the magnetic field lines going around this wire, all I have to do is grab this wire with my right hand, with my thumb pointing in the direction of the current, and guess which way my fingers wrap? In the direction of the magnetic field. So if my current's going that way, my magnetic field wraps around like this. Okay? We're going to come back to that. We just need that for this next quick example. Yep.
So is that why, like, the cord on a pair of headphones will interact with the touch screen?
Mm-hmm. Unless they've done something in there to block that magnetic field, but sometimes they do. These don't have any shielding or anything, so next time I'll be able to show you the magnetic field around the current carrying wire. But let's see what would happen with this particular device and see if we can figure out what this is. So let's say I've got a wire and I'm going to set it up like this. So we're going to look down on this, so it's like a top view. And I'm going to send a current this way. So it's going around like that. The one extra thing I'm going to do is on this part of the wire, I'm going to make it kind of like a fuse. So it's a little bit different there, but still it's current carrying part. So my current comes around like this. If my current's going through that wire, there will be a magnetic field around it. What is the magnetic field like in here? Which way does it point? if I grab this with my, so I'll use this pen in this case. So let's say if I look at the bottom here, there's my current running that way, so I grab it with my right hand like this, and notice across the top, my fingers point in. If I do it this way, notice underneath, well, it's hard for me to do, my fingers point in. So all through here, what I'm going to create is a nice magnetic field in. Okay? What we're going to do is set this up, this fuse type setting, so that it will vaporize if I send the right current through it. So eventually it's just going to vaporize. And then I'm going to stick something right here. Again, this is a top view. What's going to happen to that thing? Well, let's see. I've got charges going this way. And current, we talked about that as far as positive charges moving in the direction of current, so let's do it like that. I've got positive charges going this way in a magnetic field that's that way. There's moving charged particles in a magnetic field. There's a force on those. What's the direction of the force? So field into the board. Which way are my particles going? Down. Which way is that force acting on that part? That way, right? What happens when this is not locked in place here and here, but this vaporizes? What happens to that guy? Which way was our force? That way, right? So what happens to this? Off it goes. Anybody recognize this yet? I don't know if you've even heard of this. Oops. That's a railgun, which are pretty spectacular. So I found some videos to show you a little bit more about this.
So this is why you wouldn't talk to me about building a railgun, because this is what we had to get to?
Yep.
Okay.
This first clip is a little dated. It's an old Discovery Channel show in the early days of this, so he'll talk about some dates and things like that. But it does a good job kind of basically describing these rail guns. It chops off at the very end for some reason, but then I'll show you some other clips here in a second. So once this gets fired up, and again, sorry about this part here, getting in the way of everybody. I'll show you what you can do, or what's possible with just a simple thing like this. I'm going to cut the lights out here. Or actually, do you mind catching the lights for me? So I get this set up, so hopefully this sounds okay. So this one's about 3 minutes or so. Again, it's a little bit old, but it has some good information.
Right now, scientists and engineers are working diligently around the clock to develop a gun for the Navy that can fire a projectile at nearly Mach 8. That's right, almost 8 times the speed of sound. Dahlgren in Virginia is home to the Navy's 8 megajoule electromagnetic railgun. By the end of 2007, the Navy plans to start working with a prototype that is 4 times more powerful.
1, 3, 2, 1, fire.
The high voltage is created by charging up a bank of capacitors. Tom Boucher is test director.
This is our single shotgun. This is our current railgun that we use. It's rated up to 8 megajoules of capacity. There's an upper and a lower rails fully contained within this steel container. We actually have 220 of these 500,000 pound rated bolts, and they've been pre-stressed to hold everything together. Yet we can put enough current through this that if we don't carefully manage it, it would still come apart. We have huge amounts of forces we're dealing with here.
When the bank of capacitors discharge, A surge of current creates a massive magnetic field. This accelerates the metal projectile to mind-bending speeds. The Navy's goal is to develop a 64 megajoule electromagnetic railgun by 2016. That's 8 times more powerful than this prototype, reaching projectile speeds up to 5,000 miles an hour.
Basically, one ship offshore will be able to cover an arc of essentially 400 nautical miles in diameter. So you can essentially have the special forces guys on one side of the battlefield and a major operation on another side, and we'll be able to cover all those with one gun and one ship.
This technology is so impressive that the Navy's actually planning on developing rounds that don't have warheads. That's because of the massive kinetic kill energy available to you at impact.
The railgun comes in without explosives, but it's coming in very fast, and it's able to spread damage over a wide area by dispensing pellets, BBs. Think of a shotgun. You can dispense those and use the kinetic energy to damage soft targets, radar bands, planes, infantrymen. And so that's how you would attack the softer targets. The harder targets, you would leave the projectile intact. It would go into buildings and bunkers pretty much as a unitary projectile, and then the kinetic energy of impact would destroy those targets.
The Navy wants to equip its new generation of electrically powered ships with this weapon, but there are hurdles for the scientists to overcome. The capacitors are bulky and the heat generated is enormous. But the Navy's confident it will find a solution and make these guns a...
It cuts off a little quick there, but so they've been working on some of the issues, and so I found a little bit more of an updated thing. So they're still working on these things. Here's a newer version, so about a 1.5-minute clip. So that's firing those things with a magnetic force, which is much more powerful than, you say, gunpowder or something like that, that's more typically used to fire projectiles. One more that actually gets to some things from later in the semester. They talk about mirrors and stuff like that. So it's actually talking about how they do the video work, but it's got some kind of cool pictures, and they're using a railgun as an example. But some pretty spectacular pictures of the projectile, so, or videos of that, so I thought I'd show you this one too.
I did a video called US Navy Railgun, and in that video it shows a railgun firing a projectile going lengthways across the screen at up to Mach 7. Yet in the footage it looks like the camera is panning around and following the projectile the whole way. Since I made that video, I had more than a few people ask the question, how can a camera track a projectile moving so fast? Which is a valid question, and I myself wanted to know the answer. So I investigated how it's done, and here's what I found out. The camera filming the projectile works by having a computer-controlled, high-speed rotating mirror in line of sight of a high-speed camera. The high-speed mirror tracks and follows the projectile, keeping it in the center of the screen best it can for up to 100 meters, relaying those images back to the camera. Now, unfortunately, I do not know which camera was used in the filming of the railgun projectile tests. I could not find that information listed anywhere in any video or article. But I did find a couple of cameras that are used for projectile filming, so that is what I will talk about. The first camera is called the hand-run mini-flight follower system, which is capable of tracking a projectile for 100 meters or more as the mirror scans a 90-degree arc, while providing high-quality images of the objects in flight. This hyperspeed camera system can track any object, small or large, such as a bullet to a rocket, which you can clearly see is enough to track a hyperspeed projectile, such as a tank round. The second camera I found is called the Tracker 2 from Specialized Imaging, which uses the same type of mirror tracking design, but looks different from the Hand-on camera. This particular camera has more of a telescope look to it, but both companies have videos showing how their cameras can track tank projectiles being fired at hyperspeeds.
That's
Now,
pretty
it's
impressive.
important to understand, both cameras stay stationary. It's the mirrors that move and track the projectiles. There are other camera brands on the market that have the same characteristics and tracking capabilities, but these two seem to come up the most when Googling high-speed projectile tracking cameras. Now, I did find one other camera system which showed the camera mirrors in action. It was made by Ishikawa Oku Laboratories from the University of Tokyo. They showed a couple of videos how the camera can track a ping pong ball in real time, keeping it centered in the middle of the screen. And like the previous two cameras, the cameras stay stationary, while the mirrors do all the work tracking the object. So, I hope this helps you understand how footage like this is filmed. I know it helped me. Anyway, that's the end of this video. Thanks for watching, and we'll see you next time.
By the way, on this last little thing, again, you can see how powerful those rail guns can be as they shoot them through all these plates. So again, the mirror stuff we'll talk about a little bit later, but it's kind of interesting to see how they use that to do this really high-speed video stuff on projectiles. So it's probably a good spot to stop, and what we'll do is we'll pick up and talk about some more devices that you can make using some of the basic concepts we've already learned. So any questions from today?